All right, so we are going to start some stoichiometry in this video. So we're going to start the first lesson off with all of our qualitative stoic, and then the next step is where we're going to start to get into all of our math. So when it comes to stoichiometry, one of the things that we look at doing is identifying some unknown solutions, right? So in bonding and in solutions, we talked about some different properties and some things like that. And so now we're going to start to bring some of those pieces together, and we're also going to start to look at some additional pieces. So one of the things we do is we identify some unknown solutions. So if we were actually at school, you'd be getting a test tube. Everyone would get a different test tube, and it would have a different solution in it. And part of your task would be to try to figure out what the cation and what the anion is inside of that solution. So we kind of have three different things that we can do to help us try to identify what some of those ions are. So one of them is to do a flame test. Okay, a flame test is going to allow for us to identify the metal ion. The reason a flame test does that, or I guess I should say what you do in a flame test, is you take usually like a little popsicle stick and you soak it in your solution containing your compound. And then obviously you want to make sure that it's well and soaked, because you don't actually want to light the popsicle stick on fire. But what we do want to do is hold that popsicle stick with the solution over the Bunsen burner, and then we see the different colors in the flames. Okay, so if you've ever done like a campfire, sometimes you buy those little the little packages, and then you like sprinkle them on the fire, and they make the fire different colors. That's basically like a flame test. So if you go into your data booklets, okay, at the bottom of page 6, so underneath where you have your solubility table, you're going to find that there's this little table here that says flame color of elements. So what you find is that all of these elements, you'll notice they're all metals, produce different colored flames when we stick them into the fire. So for example, if I have lithium, I would see that the flame would turn red. And if I had sodium, it would go yellow, and potassium, it would go violet. We do have some that do produce the same colors, right? So rubidium and cesium and potassium all do violet, right? This is like if you ever watch fireworks and there's different colors fireworks, that's because there's these different metals inside of them. So if I take my unknown sample and I kind of hold it over my Bunsen burner flame and I see a color, sometimes I can either narrow it down, or sometimes I can even be like, hey, this is the only one that's actually that color. I for sure know what that is, okay? So that is one thing that we can do. We can do a flame test, okay? It's only going to allow for us to determine what the metal is, but that does at least start to narrow it down for us. Okay, the next test we can do is we can use litmus. Why we would use litmus? Well, sometimes our solutions that are unknown either contain hydrogen ions or hydroxide ions, right? And we've talked about both of these ions before, and we've said that hydrogen ions are acidic. So we would see that the blue litmus would turn red, and hydroxide is basic. So we would see that the red litmus would turn blue. So if I see a positive test, then I can determine that I either have hydrogen ions or hydroxide ions. If I don't, then I know that those are also eliminated from my possibility. Okay, the next potential test that we can do is a precipitation test, right? So we've talked about precipitates before. You saw them last year in grade 10, right? A precipitate forms when we mix two aqueous solutions and one of our products is a solid. So if I mix two things and I see that I got a precipitate, I can go to my solubility table and eliminate some things, right? If I know it formed a precipitate, I can take all the things that shouldn't have formed precipitates and take those off of my list of potentials, right? Or vice versa. If I saw there was no precipitate when I added something, then I could eliminate those ions that I know should have precipitated because they're not going to be a potential. Okay, obviously when you do these identifying unknown solutions, we don't just kind of leave you with nothing. We usually give you a starting point of it could be one of these cations or one of these anions, right? And then you're trying to identify the cation and the anion from a list of so many, right? It's not just like it could be anything. Try to figure it out. Okay, this was not supposed to be the next slide. Hold on a sec. Okay, here we go. This is the right slide. So a student performed a series of precipitation reactions, flame tests, and observations of solution color tests on a solution known to contain two metal ions. Okay, that was one thing I didn't actually talk about, was the color of the solution. So if you go back to your red book again, and you go close to the back of it, here we go, this is what page? Page 11. you'll see that there is a table here. Okay, it says color of common aqueous ions. So a lot of the solutions we deal with are colorless. And so colorless, again, isn't super helpful, but some ions are colored. So for example, if I see that I have a blue solution and I look here, well, maybe it's chromium 3, maybe it's chromium 2, could be copper 1, could be copper 2, right? We start to narrow down some possibilities just based off of that color, right? Permanganate's another super obvious one because it has this really dark purple color. Usually you guys compare it to like purple Kool-Aid. Hopefully if we're back to school next year, when we are in Chem 30, you'll be able to do a titration with that permanganate and you'll see that really dark purple color, okay? But that's another property that we can also use to help identify what a solution is. Okay, so the student does not know the identities of the ions. Use the data collected by the student, the information provided to identify the 2 metal ions present in the aqueous solution. So we have 2 different metals that are there and we need to try to figure out what they are. Okay, so we have some different evidence to help us with that, right? So we have the solution color. We're told that it's colorless. So from that, we basically know that every single metal ion that's on this table here of color of common aqueous ions isn't the metal in question because these all have a color associated with them. So it can't be that. It has to be some metal ion that is not on there, okay? So it talks about effective adding sodium hydroxide, right? So that's, did we make a precipitate? It talks about a flame test, right? So we see the flame color is red. So based on the fact that we see the flame color is red, if we go back in here to where we have our flames, right, we can look at this and we say, okay, red. So if it's red, it could be lithium, maybe calcium, but it wasn't described as a yellowish red, it was just described as red. Or it could be strontium, which is scarlet red. So we have lithium and strontium, which are some potentials here that we have, right? So from this color here, we're saying it could be a lithium ion. Should have just used the type option. Let me change over. Or it could be a strontium. Whoa, okay, that did something weird. Okay, it could be that strontium ion, or it could be, I'm still at superscript, the lithium. Those are both potentials based off of that color, right? It then talks about adding something else and getting a precipitate and then doing some flame tests on it, right? So again, we were told that there was 2 metal ions just based off of the red. We already have narrowed it down to that strontium or lithium. So different colors are going to help us do different things. Okay, I think it asked you a couple of questions, right? So list all the possible ions that give a red flame test and a precipitate in the presence of hydroxide ions. So we've already established that lithium and strontium would give us the red flame test. Now it's talking about a precipitate with hydroxide. So if we go to that solubility table and here's hydroxide, and we look, well, lithium is a group 1 ion, so it would not have precipitated, but the strontium would have, right? So list all the possible ions that give a red flame test and a precipitate. Basically, that's just that strontium ion, right? And then list all possible cations that give a red flame test and a precipitate in the presence of a sulfate ion. So same deal, we find the sulfate. Again, we still have that strontium ion. Okay, so the last one, if all traces of the 2 metal cations are removed from the solution, what might the flame color be? Well, if we don't have those cations anymore, we shouldn't really have a flame color because the flame color is simply due to those metal ions. Okay, so yeah, normally in the lab we would have some standards for you so you could kind of see what those colors look like. And then you would take your little popsicle stick, you would burn it, and then you would try to match it. Sometimes you narrow it down to 1 cation already, sometimes you narrow it down to 2, and then you could do some precipitation tests to try to help figure out what that next thing is. So if we look at precipitation reactions, right, because that was one of the things we talked about as well. So a precipitation reaction occurs when 2 aqueous solutions are combined and we create a solid product. Right? So generally, these are going to be double replacement reactions. And then, yeah, we check the solubility table, right? Because that's how we determine the states of our products. and one of them is going to come up as a solid, and that is going to be our precipitate, right? So when we are trying to identify unknowns, we know what we've added, right? And normally you're going to find we add a group 1 something, okay? And the reason we tend to add a group 1 something for a precipitate test is when you check your solubility table, group 1 ions are always soluble. Okay, they're always soluble. They're never not soluble. So then, like, if I add sodium hydroxide, let's say, and I see a precipitate, I know it has to be the hydroxide part that precipitated. I don't have to be worried of, well, now I have to check 2 spots. I have to see, did the sodium precipitate with something and did the hydroxide? By using that sodium, we know it won't have precipitated anything. And the only possibility is that that hydroxide precipitated something. And so it kind of narrows down, okay, now when I go to my solubility table, I'm only looking at that hydroxide, or the other example that was in the previous question was a sodium sulfate. So now, okay, I'm only looking at the sulfate column, and then I'm looking below it to try to narrow some options down, okay? So that's how your precipitation reactions work. This kind of leads us into the next major concept, which is going to be our net ionic equations, okay? So net ionic equations really link into those precipitation equations. They're also something that we write quite a bit of when we get into the Chem 30 and we are doing redox. And that's because what a net ionic equation does is it only shows us the things that have changed. It doesn't show us things that haven't changed. So we have a couple of steps to eventually be able to get to a net ionic equation. Generally, you're going to find that you kind of still have to go through all 3. Partway through Chem 30, you'll eventually reach a point where you feel really comfortable and you don't have to. But yeah, so our steps. First step, which is a step everyone can do, hopefully, is to write a complete balanced equation, making sure that you have all of your states, okay? Those states are going to be really important because they decide what we do in some of the next steps. So usually you're going to know the state of your reactants because it's going to tell you. Most of the time they're going to be solutions, so you're going to put them as aqueous. And then to figure out the states of your products, you're just going to go to your solubility table and figure out from there what the state is. So next step is to write a total ionic equation. So when we write a total ionic equation, what we are going to do, get this to do what I want it to do. So when we write a total ionic equation, we're going to break things apart. Okay, why we're going to do that, if you think back to when we were in the solutions unit, we talked about how ionic compounds dissociate. So even though we might write NaCl, it's really sodium ions and chloride ions. So when we're writing a total ionic equation, we're going to break ionic compounds apart into individual ions, right? Just like we did when we wrote those dissociation equations. Okay, but to be able to do that, not only does it have to be ionic, it has to be aqueous, right? Those that are precipitates are not going to break apart. Okay, so we should add, must have that AQ subscript. If they don't, you're going to leave them alone. Okay, if they're a solid, we are going to leave them alone because they're not actually going to dissociate. The other thing that we are going to break apart is going to be our strong acids. And that's because strong acids, again, if you think back to the last unit, they undergo ionization. So we're also going to break apart strong acids, just like we did in those ionization equations. Okay, everything else we're going to leave alone. Okay, so if something has a solid subscript, a liquid, or a gas, we leave those alone. Okay, we're not going to change anything about them. We're going to leave them. Okay, our last step is to write that net ionic equation. So to write the net ionic equation, what we're going to do is we're going to look at our total ionic equation. And we're looking for spectators. Okay, and that's because the spectators, we're going to eliminate them. And the reason we're going to eliminate spectators is they didn't change. So they didn't participate in the actual reaction. Right? If you think about spectators at like a sporting event, they're there, but they don't actually do anything. And it's the same idea here in a chemical reaction of oftentimes we have ions that are there, but they don't actually do anything. And the reason we need to have them is I don't just have a container of like chloride ions sitting somewhere. I have containers of sodium chloride, which I could put into solution, which would then break apart to give me sodium ion and chloride ions, but I can't just have one ion without the other, right? That doesn't happen. They always have to have those balanced charges. So to write our net ionic equation, we're going to eliminate spectators. So these are species which are identical on both sides of the arrow. Okay, so state has to be the same, charge has to be the same. If anything about them is different, then it's not a spectator. It did actually change, okay? So once we eliminate our spectators, what we should be left with is going to be that net ionic equation. So let's have a look at an example to kind of show you what that's going to look like. So if we use lead 2 nitrate and potassium iodide, so our first step is going to be to write our balanced chemical equation. So lead 2 nitrate is going to be Pb, and in brackets, NO3 with a 2. Okay, if we check our solubility table, this is aqueous. Okay, we are combining this with potassium iodide, which is Ki. It's also aqueous if we check our solubility table. So we have a compound plus compound, so that falls onto a double replacement reaction. So we are going to swap the partners around. So that means the lead is now going to go with the iodine. Again, make sure you're considering charges as you do this. So the lead has a 2 charge, iodine has a 1. So it's going to be a PbI2. Okay, we now go to our solubility table. We find iodine, which is here. We look below it, so there's most here, which isn't helpful. But we look down here, here's that lead 2. Remember when it's in this bottom row, that means that it's going to be a solid. So here, I don't want a new thing, I want to add to it. Oh, okay, so here we're going to put that solid in. Okay, then we're going to have our other compound, which is going to be the potassium with the nitrate. Because they both have a 1 charge, it's just going to be KNO3. Okay, check the solubility again. In this case, I have a group 1. I know it's going to be aqueous, but you can definitely still go. Check your solubility table. Here's that nitrate. Here's most. And potassium nitrate is not down here, so that must mean that it's going to be aqueous. Okay, next thing I need to do is I need to balance this because this is not balanced. So we need a 2 for the Ki to balance out the I's. And then we need a 2 for that KNO3 to take care of the potassium and the nitrate. Okay, so this step everyone should be comfortable with. It's literally just write a balanced chemical equation and include your states. So step number 2 is going to be to write that total ionic equation. So when we look at this equation, this is ionic, this is ionic, this is ionic, and this is ionic. So next thing we're going to do is we're going to look at states. This is aqueous, this is aqueous, this is not, this is solid, and this is aqueous. So what that means is because the lead nitrate, the potassium iodide, and the potassium nitrate are all ionic and aqueous, we're going to dissociate them. But the lead iodide, because it's solid, we're going to leave it alone. So if we were to dissociate that lead 2 nitrate, we would say that we have a lead ion, right? So a Pb2+, because that's the charge it has. It's going to be aqueous, right? Because if we were writing the dissociation equation, it would be aqueous. Okay, then we're going to do plus, and then we have the nitrate. We have brackets with a 2, so that's telling us that we have 2 of these nitrate ions. So we have to make sure that we account for that. Also going to be aqueous. Okay, so here we've dissociated the lead nitrate. The next thing we need to do is do the same thing with that potassium iodide. So notice how we had the 2 for balancing in front. We're going to have to make sure that when we dissociate the potassium iodide, we don't just lose the 2. It's still going to have to be associated with both of those. So we're going to have plus 2 potassium ions, right? So 2K plus, going to be aqueous because it was aqueous before. Okay, then we're going to do plus 2 of our iodide ions. Okay, and then that's all that we have for our reactants. So now when we get over to the product side, the PbI2 was solid, so we are going to leave that exactly as it was. So just PbI2 solid. Okay, nothing about it changes. So anytime you have something that's a solid, a liquid, or a gas, we leave it alone. We don't modify anything about it. Okay, and then we're going to have the potassium nitrate. We had 2 of them again for balancing purposes. It's aqueous and ionic, so we're going to break this apart into 2 potassium ions and 2 nitrate ions. Okay, so that's our total ionic equation. So we've basically taken this and we've dissociated that into those 2 things. We've taken the potassium iodide and we've dissociated it into its 2 things. The lead iodide was solid, so we left it exactly the same. We didn't change anything. And the potassium nitrate was aqueous and ionic, so we broke it apart. So now we're actually ready to start getting to that net ionic equation. So we're going to look at this and we're going to start figuring out what are spectators and what can we eliminate. So I start with the lead simply because it's the first. It's Pb2 plus Aq. So I can eliminate this if I have an identical thing over here. I don't, right? The lead is lead iodide. That is not the same. So I can't eliminate that. Move to the next thing, 2 nitrates. Well, here's 2NO3 minus Aq, and here's 2NO3 minus Aq. It's the same on both sides. So we're going to cancel that out. It was a spectator. Okay, the next thing we have is 2K plus Aq. And again, here's 2K plus Aq. So that means that was a spectator as well. We're not interested in it. Then we have 2I minus. There's no 2I minus aqueous over here. So what we are left with is our net ionic equation. So when we want to write that, we would write Pb2 plus Aq plus 2I minus Aq turning into Pbi2 solid. Okay, and it's just going to look like that. Okay, so one more example, just because this one looks a little different. This is number 8 off the net ionic equations booklet. So this one is different because it's not a double replacement reaction, right? When you look at it, we have cadmium metal being added to a solution of cobalt-3 nitrate. So steps are still going to be the same. We're still going to start with our balanced equation. So cadmium metal, anytime you have a metal, it's just whatever that element is with a solid subscript. No charge, right? Because metals are elements and they don't have charges. So it's going to be the cadmium plus the cobalt. Tells us it's a 3 nitrate. So in brackets, nitrate, and then we're going to have a 3. The question also tells us that it is a solution. So I don't even have to go to my solubility table yet. I know it's going to be aqueous. Okay, so we look at this. This is going to be a single replacement reaction. We are going to make the cobalt as an element, right? So going to be CO solid, and then we are going to make the cadmium nitrate. So when we find cadmium, I want to say it's a 2 charge, it is. So it's going to be CD, then brackets, NO3 with a 2. Okay, we want to go check our solubility table for that. So here's the nitrate. There's no cadmium nitrate down here. So that means that this is going to be aqueous. Okay, we need to balance this, right, because it's not balanced right now. If I look at the nitrates, I have 2 on this side and 3 on this side. So we're going to throw a 2 in here, and we're going to throw a 3 here. And then because of that, we're going to need a 3 with that cadmium and a 2 with that cobalt. Okay, so there's our balanced chemical equation. Our next step is going to be to write that total ionic equation. So why this one is a little different is we have an element. When we have an element, we are not going to do anything to it. So it's going to stay exactly the same. So it's just going to be 3 CD solid. Okay, we don't add a charge to it. We don't turn it aqueous, because if you like took a silver necklace, let's say, and stuck it in water, it doesn't suddenly turn into silver ions. Or you go back an hour later, it's still a silver necklace sitting in water. So the elements are going to stay exactly the same. But then our ionic compounds, as long as they are aqueous, which in this case they are, we are going to dissociate. So we're going to make 2 of those cobalt ions. Not hitting the right buttons. And then we are going to make how many nitrates? So the nitrate, we have a 2 in front, and we have this 3 subscript. So 2 times 3 is 6. So we're going to do plus 6 of those nitrate ions. Okay, and that's all we have on the reactant side. So we go over to the product side. We're starting with that cobalt, Same deal, it's a metal, it's an element, so we're going to leave it alone. So we're going to have that 2CO solid. Okay, then we're going to take that 3CdNO32 and we're going to break that apart because again it's aqueous and ionic. So we're going to have plus 3 cadmium ions, so 2 plus because that's what our periodic table tells us. And then we have 3 times 2, so still plus 6 nitrates. Okay, so same deal as before. I'm going to go and I'm going to check for those spectators. So I have CD solid. This is CD2 plus AQ. Those are not the same, right? One's a metal, one's an ion. I can't cancel those. Then I look at the 2CO3 plus AQ. It's 2CO solid. Again, they're not perfect matches. I can't eliminate them. But then I have 6 nitrates and 6 nitrates. Those are the same. So I can get rid of those. Okay, and then everything I'm left with is going to be that net ionic equation. So we're going to have that 3CD solid plus 2 of those CO3 plus. And that is going to turn into those 2C. Should make sure that that's a little low, otherwise you're going to think it's carbon monoxide. 2CO solid plus 3CD2 plus AQ. Okay, so same idea, right? We still started by writing the total balanced equation including states. Our next step was then to break apart everything that was aqueous and ionic, leaving everything else that wasn't alone. Then we canceled our spectators, and then what we were left with was that net ionic equation, okay? So this one doesn't really fall into the precipitation set like the last example we did, but this is also a type of reaction you will definitely see. Okay, so that's basically all the qualitative stuff we do in Stoic. After this, everything basically turns over entirely into unit analysis calculations.